Ja, se så att min telefon är på ljudlös.
Okay, so for our second talk today, we're happy to have Professor David Bolin, also here from KAUST, where he's the leader of the research group on stochastic processes and applied statistics. So he's going to give us a talk on regularity and numerical approximation of Gaussian random fields on compact metric groups. Almost.
Almost. All right, thanks a lot, and good morning, everyone. Yeah, so as you see, I changed the talk's title slightly because I was initially planning on giving a more kind of numerics-oriented talk, but then I thought that it might be nicer to give a bit more of an overview talk of what we have been working on in the group over the last year or so. So this is joint work with a number of people, especially Alexandre Simas, who's a research scientist in the group and who has done a lot of the hard work on this project. Also with Jonas Wallin, who's at Lund University. And for the latter parts, also with Mihaly Kovacs at Chalmers in Sweden, and my previous postdoc, Vivek Kumar. Right, so I guess most here are familiar with Gaussian processes and Gaussian random fields. So these are really important models in a number of areas, including statistics, machine learning, UQ, and others. And maybe one of the go-to models in all of these fields when you want to do like Gaussian process regression or use a Gaussian process somewhere, you have to specify a model for it, and the standard thing is to first try with one of these Gaussian Matern fields. So this is a Gaussian process with specified by covariance function. That's the form that you see here, and you also see some simulations of this process in 2D with different values of the smoothness parameter. So this is a popular model because it essentially has the three parameters that specify the important characteristics of the process, namely sample path regularity through the smoothness parameter, practical correlation range, and invariance. Right, so this is a very well-studied process when you are on RD. Now, what we are interested here is when you're not on RD. So we're interested in problems like this when you have data on networks. So to the left here, you see a popular data set of river discharge data. So you have the measurements along a river network in the Danube River Basin. And to the right, you have a very classical data set in statistics of this cholera outbreak in London, 1854. And in both these cases, if you want to model this using some kind of Gaussian process regression model, you really want to have the dependence of the data depend on, so the dependence between 2 points should somehow depend on the distance between the points, but not the Euclidean distance, but the distance along the network. So if you take 2 points on 2 different branches of this river network, the correlation distance is not the Euclidean one, but the distance that you have to travel along the rivers to get between the points. So this is the type of process that we're interested in defining. And importantly, as I said, we should measure distance along the network, and we want these to be models that are defined in continuous space, because we want to be able to do things like Kriging prediction or spatial interpolation using these models. So assuming that you have data observed at discrete locations, we want to be able to infer values at other unobserved locations in the network. So the first thing then is to specify the domain, so what the physical domain is, and this is where this compact metric graph notion comes from. So a compact metric graph is just like your standard graph. It's specified by well, if it's finite, we have a finite set of vertices, and we also have a finite set of edges that are connecting these vertices. But then what makes it different from a normal graph is that each edge is now thought of as a curve parameterized by arc length, and it has some finite length L. And then we equip this graph with geodesic distance, so the shortest path distance. So now the distance between 2 points in the graph is really that's the shortest path, the distance, the length of the shortest path that you can walk along the network. Right. So if you want to define a Gaussian process on an object like that, the first thing, I mean, maybe the easiest thing to think of would be to just take one of your standard covariance models, like the Matern covariance function, but measure distance not in Euclidean distance, but in this geodesic distance. The problem with that is that then you have to make sure that this covariance function is actually a covariance function if you measure distance in that new metric D. And unfortunately, it turns out that most standard covariance functions that you use in, like, for problems on RD are in fact not positive definite when you measure distances in this way. There are some exceptions. So for instance, if you restrict to a subclass of graphs, so-called graphs with Euclidean edges, not so important what that is, but it's a restriction. It's not any basically compact metric graph, but you get some restriction on what type of graphs that you can consider. Then this Matern covariance is in fact positive definite if you do not measure distance in the geodesic distance, but using something called resistance metric. And again, not so important what that is. What is important, though, is that even under this restricted setting, you get the restriction there. You see that nu has to be at most 0.5. And this means that you can get continuity of the sample paths of a process like this, but you cannot get differentiability. And as far as I know, there are no constructions in this framework that can give you differentiable Gaussian processes on graphs. And this is, I mean, as we heard also in the previous talk, this might not be so optimal because in some cases you know that you have some certain regularity so if you want to use this Gaussian process for, say, Gaussian process regression, you might know that you have, say, smoothness, and then you should have a process that can reflect that. Another thing that is, I would say, problematic with this approach is that this isotropy assumption might not be actually that realistic. So this is a very popular assumption when you work with models on RD. So basically saying that the correlation between 2 points in space only depends on the distance between the points. But if you are in this setting of a network, it's not as clear that is a desirable feature, especially if you think of river networks where the correlation might very much depend on if you have, say, a crossing between two rivers in between the 2 points you're measuring the correlation of or not. And finally, so this, I didn't mention what this restriction to Euclidean edges is, but this is also a bit well, restrictive. So for instance, here on the left, you have a graph with Euclidean edges, and on the right, you have one that does not have Euclidean edges. So this approach works for the left one, but not for the right one. So essentially, one restriction is that you cannot have two edges or two curves connecting 2 points that have different lengths. If you are in that setting, then this construction does not work. Right, so the goal that we have had throughout this work is to come up with a method to create Gaussian processes, possibly differentiable, on general compact metric graphs, and also efficient numerical methods for doing inference and simulation and prediction using these models. And main idea is to use this classical SPDE approach. So this is a representation of these Gaussian Matern fields that has been known for a long time, that says that if you take this Gaussian process with a Matern covariance on RD, it can be viewed as a solution to this fractional order PD driven by Gaussian white noise. And about 10 years ago now, Lindgren, Rue, and Lindström proposed to use this approach to define Matern-like Reynolds fields on manifolds. So they said that, okay, if we are on, for instance, the sphere, and you want to define a Gaussian process on the sphere, then that behaves sort of like a Matern field, you can simply solve this stochastic PDE when you replace the domain D from RD to the sphere. And this is very nice because then you do not have to deal anything with checking positive definiteness of covariance functions to make sure that you have a well-posed model, but you only have to make sure that the stochastic PDE is well-posed, and that is generally much easier to do than checking positive definiteness. Right, so the main idea is basically to extend this SPDE approach to the graph setting. So basically, consider models that are formulated as stochastic PDEs like this, but where now D is this compact metric graph. And this turns out to be very nice in the sense that in certain cases, you can actually work with these models exactly. So if you take the manifold setting that they proposed, in general, you have to resort to finite element approximations to be able to do anything with these models. But as we will see, at least for some cases, if the smoothness parameter alpha here is an integer, you can in fact do exact inference and simulation with these models. Right, so that's the idea. The problem then is that it is not immediately clear what it would mean, what that stochastic PDE would even mean on the network, because it's not clear how you would define the Laplacian on the network. So on each edge, the Laplacian should behave like a second derivative. But then the problem is that you have then these crossings, the vertices in the graph, and there you basically have to make a choice of how you kind of connect the edges together. And a popular choice in the physics literature are the so-called Kirchhoff conditions. So this says that basically the boundary conditions or the vertex conditions are that we should have continuity, and we have this sum to zero constraints on the directional derivatives going into the vertex from the different edges that are connected. And this is, in many cases, a very natural condition, and it's also a natural generalization of the Neumann boundary conditions if you're on RD. So, I mean, if you have a vertex of degree 1, this condition is simply reduced to the Neumann boundary conditions. Right, so to begin with, we let this delta gamma denote the Laplacian equipped with these vertex conditions. And this operator then has a quite nice domain. So it's simply, the domain is simply the functions which are twice weakly differentiable on each edge, and which satisfy these Kirchhoff conditions. So they satisfy the sum to zero constraint on the derivatives and the continuity. Right, so with this, we could then define what we mean kind of by a Matern field on the graph. So we consider this shifted Laplacian. So for now, kappa is just a constant parameter. And then we define this fractional order equation where the fractional power here is understood in a spectral sense. And I will come back to that a bit later, some more details on that. Now, so in this case, this Kirchhoff Laplacian, it's well studied in something called quantum graph theory. So this is a quite well understood operator. So because of this, we, for instance, know things about the spectrum of the operator. So it's not difficult to show that this equation is well posed. We have a unique solution that is in L2 as long as the smoothness parameter alpha is at least a half. And this solution then is in fact just a centered Gaussian random field, the covariance operator L to the power of minus alpha, and it has a corresponding covariance function that we can denote by rho. So, okay, so now we have defined a Gaussian process on the network, and we know that this is well posed, but we can in fact say a lot more. So one very important property that this model has is the following, that it is essentially invariant to adding or removing vertices of degree 2 in the network. So suppose that you have your river network and you add the vertex somewhere in the middle of a river, and you consider this equation on that extended graph where you have added that vertex. Then these two models will in fact have the same covariance function. And the same holds then, of course, if you have a network that have some vertices of degree 2, then you can remove all of those and you will not change the model. And why this is important is because in statistics, then you typically will have observations on the network. And what this essentially says is that you can add all observation locations or all locations where you want to predict the process as vertices in the graph without actually changing the model. Another thing that is also important is that this, what I've been calling a smoothness parameter, so this parameter alpha, the fractional power of the operator, is in fact a smoothness parameter. So this will determine the Hölder continuity of the sample paths. And if you increase alpha further, so if alpha becomes greater than 1.5, then you also start to get differentiable sample paths. And well, if you keep increasing this parameter, you will also get higher order differentiability. And essentially what this long text is saying is that you also have some continuity properties of those derivatives. So in particular, the even order derivatives will also be Hölder continuous. So that is nice. So this essentially means that these models behave very similarly to the popular Matern fields in RD. And here you can see two examples of this process. So here we have a simple graph with just 4 edges and 4 vertices. And to the left, then you see a simulation in the bottom of this model with alpha equal to 1. And to the right, you have a model with alpha equal to 2 that then should be smoother theoretically, and it also looks kind of like you have smoother sample paths in this case. And in the top, you see the corresponding covariance function. So this is showing then the covariance between one point and the midpoint of that middle edge, the covariance between the process at that location and all other locations in the graph. We can also say things about more statistical properties of these models. So as long or as soon as you want to do theory for, say, likelihood or say maximum likelihood inference for processes like for Gaussian processes, a crucial concept is equivalence of Gaussian measures. So we have the following result that basically says that if you take 2 of these different Whittle Matern fields with different parameters, so you have, and then we have one process with parameters kappa, tau, and alpha, and another process with kappa tilde, tau tilde, and alpha tilde. And then you look at the corresponding Gaussian measures that corresponds to these 2 processes. These will be equivalent if and only if the smoothness parameters are the same and these precision parameters tau are the same. So what that immediately tells you is that since the kappa parameter there does not influence equivalence of or orthogonality of these Gaussian measures, you should not be able to estimate that consistently in a maximum likelihood setting. So what this next result says is that essentially, well, we cannot estimate this kappa parameter, that is basically the practical correlation range, consistently. But for a fixed value of the smoothness parameter, you can estimate the precision parameter tau consistently, and the maximum likelihood estimator of that also has some asymptotic normality properties. This is exactly how the Gaussian Matern fields in RD behave like. Finally, we can also say something about predictive accuracy of these models. So, as soon as you see this result that you cannot estimate all parameters consistently, you might be worried, because if you use this model for prediction, then typically what you do in applied problems is that you fit this model to data, so you estimate the parameters, and then based on these estimated parameters, you say infer the value or the values of this process at unobserved locations. And if you estimate the parameters first, then this kind of optimal prediction that you make will depend on the parameters. And if those are misspecified, these predictions might be inaccurate, because you are doing the prediction under misspecified parameters. But essentially what this last informally stated theorem says is that we do not have to worry about that. So in fact, asymptotically, as you get more data, the only parameter that will matter for the quality of spatial predictions is the smoothness parameter. All right, so, and again, this is the same type of behavior as you see for Gaussian Matern fields in RD. Right, so this basically means that we have good control over both kind of theoretical and statistical properties of these models. But so far, I have not said anything about how you can actually work with these for real data. So if you want to, for instance, do maximum likelihood estimation, one thing that you must be able to do is to compute the likelihood of the data under this model. And for this, you must be able to evaluate then finite dimensional distributions of this Gaussian process. And this is not so easy to do because, well, the model is specified as a fractional order stochastic PDE. So it's not immediate how you would actually do that. But it turns out that we can, and this is what I said in the beginning, that as long as this smoothness parameter alpha is an integer, we will be able to do this exactly. And the reason for that is the result that you see there on the top, that says that if you consider this model, this model has Markov properties, so it's a Gaussian Markov random field, if and only if this parameter alpha is an integer. And this Markov property we can then use to derive finite dimensional distributions. And the idea is for how we do this is quite simple. So because we have this kind of Markov property, one idea would be that we should be able to represent this process by, so suppose that you are on this square graph here. We should be able to define some independent Gaussian processes for each edge. So we basically split this graph into 4 individual lines, and we define for each line an independent Gaussian process. And then we tie them together by conditioning on these Kirchhoff conditions. So for alpha equal to 1, this would just basically mean that you define some Gaussian process for each edge, and then you condition on the fact that they should satisfy continuity at the vertices. And for alpha equal to 2, we would then condition on continuity plus this sum to 0 constraint on the derivatives. The question then is just how should you define this independent processes ui in such a way that after you condition on the Kirchhoff constraints, you obtain a solution to this SPDE. And the solution is a bit well, here it is. It's a bit involved, but essentially what we do is that for every edge, you can take your standard Matern field, so a Gaussian process with a Matern covariance, and you consider the multivariate version of that, where you look at the Gaussian process and all of its derivatives. That process has a covariance function, this boldface R, and then we do not actually consider that process, but a correction of that. So the covariance function that we will consider is this R tilde, that is the covariance of the Matern process and its derivatives, adjusted by the second term. And if you define this multivariate process for each edge, and then you condition on that these should satisfy these Kirchhoff conditions, and then you look at the first entry of that process that you get, this would be a solution to the stochastic PDE. Right, so this looks very involved, but in fact, it is very easy to implement in the sense that now the advantage is that you know the covariance function of this process on every edge. So because of that, you can actually easily now compute likelihoods, because, well, you know, if you know the covariance of a Gaussian process, you can compute the solution. So more specifically, so what this means, so first of all, this conditioning that we're doing, this is just a linear constraint on the Gaussian process. You can formulate it like that. And because this, the process, as we saw before, this is a Markov process, so if alpha is an integer, what we're essentially saying is that this process can be viewed as a Gaussian Markov random field under linear constraints. And this is something that is quite well studied in statistics. There are many methods for doing efficient computations with Gaussian Markov random fields under linear constraints. So this is in fact what we have reduced this kind of fractional order stochastic PDE to just a Gaussian Markov random field under linear constraints, which is something we can essentially use standard methods to deal with. So in fact, for alpha equal to 1, we get an explicit precision matrix. So this Q is the inverse of the covariance matrix of the process evaluated at the vertices of the graph. And again, this looks a bit involved, but that's what it is. It's just summing over, for every vertex, it's summing over the edges that are connected to the vertex. The crucial thing here is that this matrix would be very sparse. And this sparsity we can use to essentially use this model for big problems. Another thing to note here, so as I said before, is that you can add vertices of degree 2 to this model without changing the model. So the fact that you can evaluate finite dimensional distributions in the vertices is actually enough, because then if you want to evaluate finite dimensional distribution at your observation locations, you can just add those as vertices. All right, so let's see how this works in practice. So here we have a small application. So what you see here in the figures, this is traffic speed data from highways in San Jose in California, and what we basically did is that we took this data and we fitted some different models to this data, and we compared their accuracy in terms of predictive performance. So we considered this isotropic exponential model that I mentioned in the beginning, these Whittle Mat fields with different values of the smoothness parameter, and some discrete models that are based on the graph Laplacian that, well, they are essentially not continuous space process models, but they have been used before to study data of this type. And long story short, here are the results. So we fitted all of these models to the data, and then we evaluated their predicted performance through cross-validation. And in the table here, you see these 5 models and a bunch of different measures measuring the quality of the predictions, so root mean square error, mean absolute errors, and some proper scoring rules such as log score and continuous rank probability scores. And what you can see in this table is that this Whittle Mat field with alpha equal to 2 behaves the best in all metrics, and they are actually a lot better than the non-differentiable models. So it's in particular this isotropic exponential model. So differentiability here is really crucial for accuracy of the predictions, as we also expected from the theory. Some other comments. So this is actually an example of a graph that does not have Euclidean edges. So that top model, the isotropic exponential, is not guaranteed to be a valid model. And also, I haven't mentioned these graph Laplacian models, but essentially, you can view those as basically finite difference approximations of our continuous space Whittle Mat fields. All right, so this example was in fact done using an R package that we recently released that contains a lot of functionality for dealing with data on networks and graphs of this type, and it also implements well, all of these models that you saw in the table. And one crucial aspect with this is also that this package has interfaces to our inlab that we heard about before in this workshop, and also inlabru, which is basically an interface to our inlab. Which means that you can now take these Gaussian process models and include them in full kind of latent Gaussian hierarchical models. Right, so just a kind of to show you how I obtained those results. So here is the just our code for loading this data and creating this network for this particular data. So we have this MetricGraph object that is basically contains the topology of the network, and it also you can then also add the data to that network. And then, given that you have done that, is then easy to specify and fit the model. So this is the entire code for specifying the model and fitting it to data using this inlabru package that internally is using our inlab. Right, so we specify the top line there. We specify the model based on the graph, and then we fit the model using inlabru, and in the bottom we just extract the results. So in the lower table there you see estimates of the practical correlation range and marginal standard deviations of this model. And you can also then easily do predictions. So here is, well, here's the code for doing Kriging prediction based on this model. And in the top you see the results. And I'm not sure if you can see the color so easily, but this is a very good example to show why you cannot use a model that measure distance in Euclidean distance. Because, well, as you see in this, you have kind of in this highway, you have these different lanes, and you have very different speed in the 2 lanes. So you have kind of points that are very close in Euclidean distance that are very different values. So if you would use like a standard Mat field on R2 in this case, you would not basically be able to do anything. All right, so we could essentially stop here, right? So we have a model, we have the software for doing it, for implementing it, and it seems to be working well in practice. There are 2 things though that are a bit, well, maybe not so well, that we could do better maybe. The first thing is that here you have to fix this smoothness parameter. So this alpha parameter, it has to be fixed to an integer for us to be able to work with this model exactly. But from the theory, we knew that these smoothness parameters were actually crucial for the for doing prediction. So it would be good to be able to estimate the smoothness parameter from data. And secondly, in this model, you can, so these parameters kappa and these parameters, say kappa and sigma here, they have to be constant. So which essentially means that you cannot let the correlation range be varying over the space. That might also be a restriction. Yes.
Sorry, question. How do you describe this topology? Distance between streets, point A and B, or how it is done?
So in this case, the data, so essentially every street segment here is like it's a lines object, spatial lines object in R. And then, so it is internally, you just essentially keep track of the vertices, so where you have connections between the streets. And then internally, it is every road is essentially stored as a line, as a curve in R. So what is important is basically the connectivity, so which road segments are connected to each other, and also the length of each road segment. So that's basically what.
Thank you.
Yes, so to be able to, so unfortunately, if you want to be able to work with general smoothness parameters, as far as we know, you cannot get finite dimensional distributions exactly. So you would have to resort to some kind of finite element approximations in this case. And if you do that, we might as well consider a more general model where you can also allow these parameters to be spatially varying. So you can allow for, say, different marginal variances in different parts of the network. Right, so this is then the extension to these generalized Whittle Mat fields, where we consider a similar type of fractional order equation, except now that this operator L now has parameter kappa that can vary over space, and we can also include this parameter A, kind of like a diffusion coefficient that can also be spatially varying. And under these kind of assumptions of basically the boundedness of kappa and Lipschitz of the parameter A, we can show that this operator behaves well. So if you, for instance, equip it with these Kirchhoff conditions again, it is again a self-adjoint, densely defined positive definite operator with a compact inverse, meaning that it has a spectral expansion, so we can define that fractional power L to the power of beta in the spectral sense. Right, so, okay, so that's what this is essentially saying, that this operator, if you define it in this way, it has an eigenexpansion, and we also have a Wiles law for the eigenvalues, so we know how the eigenvalues essentially behave. So because of this, we can then define the fractional power in the spectral sense, as well, this is just standard, how you define the fractional power in the spectral sense. Now, if we want to extend the results that I showed before, such as looking at sample path regularity for this model, one important thing then is to understand how these H dot spaces behave like. So this is one of, so again, not going into so much details here, but this is one of our main results in characterizing the domains of these fractional order operators of this form. There are two things to take away from this slide. The first thing is that this H dot spaces, the domain, behaves actually as you might expect. So what this is saying is basically that the domain is again something that is kind of H beta, so fractional order Sobolev on each edge, intersected with possibly continuity and this sum to zero constraint on the derivatives, depending on what beta is. So that is very important for understanding how these models behave like, but also for deriving results later on for, say, when we do finite elements and want to do convergence analysis. The second thing that is important is the last row, that is essentially a Sobolev embedding result for compact metric graphs. So based on these things, we can again show that we have a unique solution as long as we have a large enough smoothness parameter. So as long as the smoothness parameter is large enough, it is in L2. It satisfies the same invariance to adding or removing vertices of degree 2. And we have the same type of, so this smoothness parameter that I know that now changed to beta, it was called alpha before, has the same role as in the easier non-generalized case. So it determines the Hölder continuity of the sample paths and the differentiability of the sample paths. All right, so as I said, we have not figured out how to work with this model analytically. So we have to do some kind of numerical approximations to work with this if we want to implement this in the computer. And we do this based on finite elements. So we consider now a finite element space over this network. So it is essentially just a collection of finite element spaces on each curve, in each line. So we just use the standard hat functions. The only kind of special thing in this case is that we will have these finite element-based functions at the vertices that are essentially hat functions that extend into many different edges. And then, well, we can do the standard finite element procedure, right? So we define a discretization based on the bilinear form of this operator. And we consider then the finite element approximation of this solution reads like this. So then we would solve this finite dimensional problem to find UH, which is our finite element approximation, where WH is now finite dimensional approximation of the Gaussian white noise. So this is quite standard, except now that you have this LH beta, so you have a fractional power, so you have to deal with this fractional power somehow to get to something that you can actually implement in a computer. And there are actually many proposed methods for doing this. So you can, for instance, use the Bonito-Pashek quadrature approach for doing it. That basically reads like this, that we approximate the inverse of L to the power of beta using a quadrature, basically like a quadrature approximation of a Balakrishnan representation of the fractional power. And then you can basically take that quadrature approximation that, as you see, is just a weighted sum of non-fractional inverses that you can actually implement easily in the computer. But you could also choose some other methods here for handling the fractional powers. So as long as you have a method that is exponentially convergent, you can actually choose any. So we, for instance, have another rational approximation that we have also implemented that essentially has the same theoretical properties, but actually works better in practice. So if you do that, we have results like this. So basically, you have the control over the both strong error of this finite element approximation and also of the error of the covariance function of the finite element approximation. So if you calibrate essentially this the order of the rational approximation with the finite element mesh width, you get strong convergence rates. That is essentially what you would expect. Right, so just some numerical results here to illustrate that. So here is again a quite simple graph. that we looked at. So we take this model, we fix just kappa to be constant, and then we look at this solution for different values of the smoothness parameter, and then we look at, well, different meshes, and for each mesh we choose this essentially quadrature step size. We calibrate that so that we get, theoretically, we should have this convergence rate that you see here. And well, in practice, that is also what we observe when we implement this in the computer. So both the strong errors and the covariance errors numerically correspond very well to what we got theoretically. Right, so that works, and we have also implemented this. So we have this other R package called RSPDE that contains a lot of methods for dealing with fractional order stochastic PDEs. And among other things, this package can be combined with this MetricGraph package to implement these models. And again, this has an interface to our inline inlabru, so you can also define these fractional order models and include them in general Bayesian hierarchical models. Right, so again, going back to the data, here's the same slide as before, how we define this graph for this traffic data. And here is now the entire code for fitting this fractional order model to the data, where we also estimate the smoothness parameter. So what you then have to do is that you have to start by computing these standard finite element matrices that are needed for the approximation. And then you define the model, you fit it using inlabru again, and we extract the results. And in the bottom table there, then now you see that you have estimates of the standard deviations, the practical correlation range, and also this parameter nu, that was the name that was used for this smoothness parameter in the maternal covariance in the very beginning. So we got an estimate of nu that was around 1.5, which in fact corresponds to alpha equal to 2. So that model that we fitted in the non-fractional case that we saw alpha equal 2 gave the best results. It seems like this is confirming that that choice for the smoothness parameter was indeed a good choice. All right. So in summary, so what we have been working on is this construction of Gaussian processes on networks and metric graphs. And as far as we know, this is the first construction of Gaussian fields that can be differentiable on general metric graphs. We have known both sample path and statistical properties of these models. And in these Markov cases, where we have an integer smoothness parameter, we can actually do inference exactly. But in general, we have to resort to finite element approximations. But in that case, we also have kind of control over the accuracy of those approximations. So if you have some data of this type, or if you want to test these models, the package is available at this homepage, and there's a lot of documentation there also for how to use it. And well, so some ongoing work that what we're currently working on is mainly two things. The first thing is to extend this to spatiotemporal stochastic PDEs. So, I mean, what you saw here was on purely spatial models where there was no time in the equation, but for many applications, we also want to include a temporal component. And another thing is to include these models in so-called log Gaussian Cox processes. So if you have data that is essentially presence-absence data, like if you model, say, traffic accidents, then you don't really have a numerical value for like what the observations are, but it's just the fact that you have an accident or not that is the data point. And then popular statistical model for this are these so-called log Gaussian Cox processes, where we're now working on studying such models. Right, so here are the references if you want some details about all of this. So the top one is the first paper that where we introduced this Whittle Mat fields and looked at their sample path properties. The second one is introduce this generalized Whittle Mat fields and the finite element analysis. The third one is about Markov properties of these models, and the final one is the statistics, basically. Right? That's it.
Thank you very much. This was a very nice talk. Do we have any questions from the audience? Alex, please.
Thank you for very nice talk. If it's graph, assume graph is very large, does it make sense to decompose graph into subgraphs and apply one model for one half and one for another?
Yeah, that's a good question. So, I mean, yes. Actually, so what we assumed throughout here is that the graph is connected. So basically that you have correlations throughout the graphs. If you would kind of decompose it into well, it depends on how you do it then. If you, I mean, of course, you could just decompose and assume that you have independence between the two disconnected graphs, but whether or not that is reasonable or not, I think that will really much depend on the application.
Okay, thank you.
Hi, thank you very much, David. So I have a couple of questions. One is, have you considered on top of the strong error estimates, weak error estimates for the computation of expectations that depend on the solution?
Not yet. So far we have only the strong error and the covariance error. So I mean, we have some weak estimates in the non-graph setting, but we have not looked at weak error estimates yet.
What do you think that changes in the analysis from what you have already to this one?
I mean, so essentially the rates, I believe, will be, I mean, like twice the strong rates as normal, but the analysis is quite different, I think. I mean, how you derive these weak rates. So we have a paper on that in the RD setting, and I mean, it's quite much more involved than the strong errors. So that's essentially why we didn't do it, because the paper got long enough with just the strong errors and the covariance errors. But I think it's definitely doable.
Okay, great. Second question: when you have this operator L and then you take L to the beta, right? You have some assumptions on boundary conditions for L. And what does it mean when you take L to the beta? Do you have some control on what is the boundary conditions that you impose when you have this power automatically on the...
Yeah, so exactly. So that was essentially what this... so this is essentially what this theorem is saying. So we start with... Okay, so I didn't actually mention... So here I have said that we impose L with these Kirchhoff conditions. So that was continuity and sum to zero constraint on the derivative.
Yes, this is the inner edges, right?
Yes.
So when you have...
I mean, okay, okay, so here then, like the boundary here would be a vertex of degree 1, which would just be Neumann.
Okay.
Like the true boundary is a Neumann boundary.
And then
condition.
when you take powers of beta, what does it mean? I mean, do we have some intuition on
so
corresponding boundary condition that you get?
Exactly. So then you essentially so this is basically what this, well, okay, this is not really saying that, but you basically start to get these conditions on derivatives of the process as well, right? So if you take the operator to 2, then you will have a Neumann on the process and also a Neumann on the derivative of the process.
So you work with fractional, right?
Right. So if you do integers, that is what you get. If you do not do integers, then you have things like this. So then it will depend on. So these spaces are basically interpolation spaces between the integer powers, and then so basically what you see here is that you have for instance, if you go from beta from 0 to 1/2, you basically do not have any boundary conditions in the sense. And then as beta goes above a half, you start to get continuity, and then yeah, so it essentially between the halves that something is happening on what the boundary conditions are. Yeah, so I mean that is basically typically what you get when you do interpolation, right? So if you have if you take like a Neumann Laplacian and you consider interpolation between like beta between 0 and 1, beta above a half, you still have Neumann on L to the power of beta. But when beta is less than a half, essentially the boundary condition disappears.
I was asking more like, for example, when you take some higher order set by Laplacian or something like that, then you start trying to identify which are the boundary conditions you can impose, and then intuitively you understand more or less which are the derivatives or the values that you can actually impose, and then there are combinations. I mean, it's not as obvious as second order, for example, right? You start getting combinations, and here,
all right, but
it's not so obvious to me what you can impose and how you can do it.
No, but I mean,
some flexibility that I think is lost when you take the power automatically.
Yeah, I mean, there is some flexibility lost in the sense that we just impose boundary conditions on L, and then you take the power and you get whatever boundary conditions you get.
And it's not so clearly intuitive what is that is being
yeah, right. No, I mean, you could imagine that you could also somehow impose boundary conditions on L to the beta directly.
Exactly.
Yeah, I mean, so, but yeah, we do not really do that. And I think one reason is that we usually don't care so much about the boundary conditions in these statistical applications. But actually in this graph setting, it is more important. And this is also something I didn't mention here, that actually in this paper where we looked at these generalized models, we looked at a much larger class of boundary conditions as well than just this Kirchhoff.
Thank you. Are there any more questions? Well, then we just thank David once again. Thank you very much.